everybody, welcome to this third tutorial now on working with drone images and constructing 3D models of built environments. So here I've got a minor set, a small subset of 15 images acquired from the drone that we've seen demonstrated today. It's of the IIT Kanpur, one of the outdoor amphitheaters, to have some environment that's built instead of just a natural setting to kind of fit with the course's mandate on urban environments. So we're going to go through some simple and more advanced steps on how to work with these. So what we have here is 15 separate images. One of the generally first applications of drone imagery is to have a mosaic image which covers a larger area. Now I'm going to show you first a simple way to do this, again, which is free of cost. And then we're going to go into the full 3D approach. So first, let's look at something called Microsoft Image Composite Editor. So this is a free software that you can download and that we requested you download earlier. So it is one of the best image stitchers on the market, and it's free. So you don't need to go into a subscription, free trial, etc. It is absolutely free. So you just download this Image Composite Editor. Very simple to use. We're going to go New Panorama. And now it wants images. So these images are stored in the folder called GIAN Tutorial, and I'm just going to go Control A, select all of them. Right, there's our 15 images. Now we can go stitch, or we can just go to the next button here. The default options actually work really well. So now it's going to locate how the images overlap. It's going to identify the spatial location of the images on its own without me specifying anything, and actually without using the GPS coordinates from the drone. This is pure image analysis. It will see matching objects in neighboring images. We talked about this in the photogrammetry lecture. So it's, for a small set of images, it's pretty quick. It can, depending on your computer, it can handle quite big data sets. There's the result, right? So we see perhaps some undesirable areas that we'll need to crop, but you'll see there's a function for this. So let's just go to the next. This seems fine. Let's rotate this 90 degrees. Already it's almost north-south, and now let's go to the next to crop it. Right, now use a very, very straightforward and nice cropping interface. Let's just get rid of the blanks a bit, shall we? Like so, put a bit here. There we go. Let's get this building complete if we can. Something like this. Next. And then we export it. Hit the export to disk. Let's not going to call this GIAN stitch, and I'm not going to put it in the same folder. I'm going to put it in this other folder. GIAN, right. And there we go. Now, this image has no geographic location, so then you would actually need to use the methods that we've seen to give it one. So I'm just going to go ahead and close Image Composite Editor. We don't need to save, it's quite fast. I've already got QGIS open. You'll recognize the area. So what I can do very simply is go to Raster, Georeferencer, like we've done in the first tutorial. Now, apologies, on this computer the icons are extremely small, but you'll recognize the settings. So, my target coordinate system is going to be 44 north, 32, 6, 44. We're just going to do a simple polynomial transformation. Georeference, something like that. Okay. Now we're going to add our raster. Navigate through my files. GIAN stitch. There we go. Here's our image. Now I'm just going to do very quickly, maybe perhaps 3 points. I'm going to pick the corner of the amphitheater from map canvas. You remember the drill, right? Zoom in a bit. I've got the hybrid version here, so this is slightly approximate. It's just about, yeah, very inconvenient. It's right on the sea. There, it's still roughly okay. And the center of this black tower here, which is right here. And now perhaps something a bit further removed. There's a lot of options, really. let's take the northwestern corner of this little canopy which is on the roof of this building. Now I can use, remember you can use the arrows on the keyboard to move the display without having to go for the pan, which would complicate the coordinate system interface. There it is. So I can just go out here. Okay. Run this. What's en route? Raster named in stick. It's the right coordinate system, right? So reference. It's quite a high density image, so it will take a few moments to process. And there we are. We do see now there's some interesting complications here, which is why I actually bothered with this exercise. As you might assume that it would of course be better, but I wanted to demonstrate a few interesting things. Now if I zoom to layer, right, now we see that there is a definite warp, a definite twist in our image, like a parallelogram. So one of the difficulties here is that we have undertaken a 2D georeferencing operation on objects that are very, very 3D. Now it's good that we've done this because we can really see the problems that this has caused, that really has caused the warp. And that's because our objects were not all at the same altitude, our coordinates were not all in the same places. So we really need to go for a 3D approach to this. Now, you could, however, improve the quality of this by adding maybe 5 to 10 more control points, and then the things would average out to be approximately correct. So if all you need is a 2D map, I guess you could consider doing it this way, but this is a valuable exercise in that it shows why it is important when you've got large variations of topography, especially in urban settings where you can actually have a building which is 20 meters higher than its neighboring ground. You've got very high altitude variations, well, very high, big altitude variations in local areas. So this can be useful in certain cases, especially I think if you were to concentrate on control points that were on the ground, but these are often harder to find because the buildings give us the most visible reference points. So now what we're going to do, I'm going to stop the recording and I'm going to close down QGIS and we're going to go to a full 3D approach. Okay, we're back. So I've closed down QGIS and I've opened, as you saw, PhotoScan Professional, which is one of the softwares we recommended that you go for a trial. I mean, this is the one software in the course which is not open source. At the moment, there are open source software for drone 3D processing that are starting to emerge. They're almost mature. I'd recommend that you look at WebODM, Web Online Drone Mapper, I think something like that. It's coming, but at the moment, PhotoScan is still the best. It is relatively cheap for educational institutions at about $600 US. And the trial is free, so that's fine. So it will still allow us to go through the steps, and then after that you can decide for your own environment whether or not it's worth investing money or whether you want to go to open source solutions, which do exist. So this is a very simple program, really. It's quite intuitive to use. Now the first thing that we're going to do, really, the secret here is that there's a workflow, and you follow the menu items more or less in order. So we're going to add the photos. It just comes up. So these are the 15 photos that I'm using as a subset for the tutorial today. This, of course, PhotoScan can take thousands of photos, and the only limit is your computer. It can become very processing intensive. Right. Now what we've got here, say this is interesting, if you look at the main display of PhotoScan. Now we don't have any 3D image yet, but what PhotoScan has done is it has displayed the position of the drone at the time of recording the images. So we have a bit of a triangle here. So this is taken from the GPS data, which is embedded as metadata in the image. It allows PhotoScan to know where the drone was for each image. And this is what's going to give us the basic geographic reference. Now, we're going to set that geographic reference. If I go on the reference tab, we see that there's a coordinate. Now, the drone records coordinates in longitude and latitude. And of course, we've talked about this. It's not ideal. So what we are going to do at some point is we're going to change the settings to work in a different coordinate system. At the moment, we can still work with the system, and it's only at the time of processing. So you see at the moment, right, we're in 4326. For the moment, that's fine, but only for the moment. So we're going to go back to workflow, and we're going to follow the steps. You'll see the possible steps are in black, the other ones are grayed out. So we're going to align the photos. For the moment, now you should do, if you want good quality, you should do high or highest. High is usually quite good. But now in the interest of speed, I'm only going to choose medium. If you're in the field and you just collected some drone imagery and you want to instantly know if things have worked, then low or lowest will do. It'll give you a preliminary look. Let's do medium now. It should be manageable. Should take less than a minute, right? So you'll see now what the software is doing is it's actually matching key points in the photos. It's actually using artificial vision in order to find what we call conjugate points in each image. So really it's taking the set of image and it's identifying identical features in each image. This is a step that can actually take long. If you've got thousands of photos, it can take days to process. Of course, now we've only got 15, and it's actually heavily influenced by the size of your photos. So the photos that we're using now are from the Phantom 4 Pro that we saw this morning, which means that their resolution it's 20 megapixels, their size. So it does take a bit, and I've only got 15, and I'm only doing medium. If I were to do this at highest, it would probably take a good half an hour. Of course, this is just on my laptop. So it is, if you're going to do a lot of this, you need to invest in a desktop. Now, here we go. First step. We'll see that actually already we get a fuzzy cloud of the amphitheater. Now what's interesting, so now the photos, in addition to having a point location, we've actually got a rectangle. That rectangle not only gives us the position of the photo, but it gives us its orientation. So literally that rectangular plane tells us which way the photo is facing. And we can see already a basic outline of the scene with the buildings. So this is obviously quite sparse. Now we're going to densify this cloud. Build a dense cloud. I'm going to do slow. This is quite a computationally intensive feature. I'm going to do this slow for the sake of the tutorial not taking too long. It should be quite fast. Even then. So the build dense clouds phase is definitely the longest. So I'm going to pause the recording for these 2 minutes, and we're going to come back when it's done. Okay, we're back now. So the processing is finished. Now at the moment you don't see the result. Sometimes it displays by default, sometimes not. You can see up here, these options are going to become ungrayed as they become available. So now this dense cloud, multicolored points, has become calculated. And now we've really, if we look, right, we have really densified the model. Now this could actually be denser. Right. Now we're already beginning to see one of the challenges with building drone models of built environments, and that in this test flight, really, the drone was flying quite high and the camera was pointed straight down. And that means that there's a lot of occlusions occurring. For example, we have no idea what's going on below the amphitheater. Right? There's no data because the drone imagery couldn't see it. Even on the stage here, there's nothing. It's a big blank. So certainly one conclusion is that if you're going to do this full, you need to add what we call oblique images, which means that the drone camera has to be pointing at an angle, not straight down, right? But nevertheless, let's continue this. Let's continue with the steps and process. So once we've built the dense cloud, we're going to build a mesh. Now, a mesh is a 3D topological model which actually defines the surface. All you're looking at here are individual points which have colors. Now we've got choices in mesh. Now one of the first choices to choose from is arbitrary or height field. Now height field is what we call 2.5 dimensional, and that means that for each XY location on the map, you are only allowed to have one measure of elevation. That's great if you have a riverbank, if you have a farmer's field, if you have a mountain of bare rock. But if you have a complex object like a building where you could have overhangs, you could have structures, that won't work because it's quite possible that for one point in XY you have multiple objects that are self-contained. So usually for buildings what we choose is arbitrary. Now be warned, this is extremely demanding on your computer. I'm not even going to go to high here, I'm just going to go to low. It is very much consuming the RAM, and typically for urban environments I would actually say that you go up to a computer that has 256 GB of RAM, so really you need huge numbers. It's very demanding on the computer. And now we're going to generate the mesh. So once again, I'm going to pause the recording while it processes. Here we are, the mesh is calculated. If we look at this surface now, so this is of course a low density surface which has been calculated. Now you can see that the stage, we didn't have any data, the stage is closed. So this is and you have the basic shapes here, right? This would improve quite a lot if you had a powerful computer and you could put the settings on high. So this is what we call the mesh. Of course, now we can improve this. We can actually produce things that are good for visual display, and those are called image textures. So just go with the defaults. So what this is going to do is it can be known as image draping. In the beginnings of GIS, it was very popular to have a DEM and drape an image over it. So what it's going to do is it's actually going to mold the images on this 3D surface that we're now looking at. And that will, of course, add much more detail to the visual aspect of it. This process is usually quite fast. I'm hoping that I won't have to stop the recording for this. Fine. And I guess one interesting thing to note is that all this work is given a geographic coordinate by photoscan, right? We are not going to need to open this data into QGIS in order to do a manual georeferencing from the Bing map data. It's almost done. There we go. Now the texture button is this one here. Now that is starting to look much more appealing, isn't it? Now there are still warps. There are some significant warps, mainly because now the way to solve this is to add more drone images, because like I said, this is a very three-dimensional object. There's a lot of overhangs, so what we need to do in order to make this really look good is to have the drone fly much lower. You see how high the drone is flying. Have the drone fly much lower and basically take shots along the side, the facade of the building. So doing 3D survey in urban environments does need a lot of planning. Of course, you need the permission to fly there, and you need to think closely about getting all the required views of your scene, and that's going to lead to some quite big data sets. So it is a challenging field. I mean, it doesn't need to cost much, but I think the computing cost is probably the greatest. So now we've got the basic products, and now we're going to start to produce export material. So the first thing we're going to build a DEM, so a digital elevation model. Now we're going to go to planar geographic coordinates, but here we're going to choose to produce our DEM in the right coordinate system. So let's go 3, 2, 6, 4, 4. There is our EPSG. So photoscan recognizes EPSG. It's quite useful. So we're going to produce a DEM in this coordinate system. Dense cloud. Right. This is fine. The defaults are fine. We need to save the project. GIAN tutorial 3. Alright, now we can say build that DEM. At low densities, it's quite fast. And then the other thing we're going to build is the orthomosaic. So the surface we're going to use is the DEM. Now pixel size, because the drone coordinates are in lat long, the pixel size is actually in degrees, but if you hit this button here, meters, so resolution meters, 2 centimeters, we don't quite need that. But nevertheless, let's produce a nice orthomosaic at, say, 10 centimeters. That should look quite attractive. Again, coordinates. It's going to do it in geographic coordinates. There we go. 44 north. Oh, meters, here we go. 1. It's going to orthorectify the image. This can be a bit more demanding, but it's going quite well because there's only 15 images. And certainly if you have a large data set with hundreds of drone images, And note, this will work even if you have images that are looking sideways on buildings. You will still get a good map. Right, now we can actually, we can look at the quality of these outputs. I'm going to open up QGIS again. There's other things we can look at. If we go into, now in this case, we don't have any control data, but certainly PhotoScan will allow you to produce a report. Oh yes, of course, now we need to export our orthomosaic, right? So pixel size 0.1, ATM, write the world file, it's quite a big file, export. Done, so 3 ortho, 10 centimeters. I always like to write the resolution of my ortho photos in the file name, makes it easier for later. And then we're going to export the DEM as a TIFF file. Let's change the coordinates on this. Meters, yeah, 20 centimeters DEM, quite high resolution. So, DEM, 20 centimeters. And we're going to export something new. We're going to export the model, which is it's going to be a 3D object. I'm going to export it as PLY. This is a 3D object, and we might have a chat about point clouds later. So, cloud. If we have time in the practical, we can have a discussion about point clouds. This is kind of a standard processing. Right. Now, queue's open. Let's create a blank map, and let's add these rasters. So, they should be in here somewhere. So, there we go. GIAN 3, the ortho 10 centimeters. Right, and there we go. There's our ortho photo. It actually looks quite good. It recognized our coordinate system, so you can see it's quite clean. Actually, let me do something. Let me if you compare it, well, certainly you remember from the Microsoft ICE exercise how warped it was, and with the 3D approach we have absolutely no warp. It's absolutely clean, and that's because we really used a 3D process, and of course the resolution is going to be quite stunning. Right, if I zoom in, it's quite high resolution, much higher than big maps. So this is a good way to get the processing in. We can of course add the DEM. DEM 20 centimeters. Right. And here we can see the elevation coded as color. So the lower ground is black, this high building is white, the amphitheater goes from black to nearly white, works very well. And that's the process. These are really the final processes that you would go through to get from a drone photo to a 3D environment in QGIS. Now I'm going to show you one more thing in this tutorial. Now, so we're working with 3D objects. Now what I've done here is I've opened the model that we exported, so the third object that I exported as a Stanford PLY. I've exported in a program called Cloud Compare. This is a free software. It wasn't mentioned in the list we sent you. You can install it. This is more for curiosity. You might not need this, but let's see. So it's called Cloud Compare. There's also another software that I mentioned in the first lecture called MeshLab, which will do similar things, although less analytical. So what I've got here is I've got the 3D model. It looks like the ortho photo, but really, if I rotate, you see that I really got a full 3D model. Now, if we're going to be working with these inherently 3D objects, which are cities, it's actually good to have the possibility to move away from, the aerial view like this, where basically you see it. So let me look for the top view, like so. So this is a top view, and we have no sense of how the buildings are. But by working with point cloud analysis, we call it, we can really get these 3D views. See, I'm actually looking under the point cloud now. There we go. There's the top of the point cloud. So this is a very much 3D processing approach. These bits of software can actually allow you to compare two clouds throughout time, cloud compare as it's called, and this can allow you to calculate, for example, the volume of a new building that's been built, things like that. So it's quite a powerful tool for visualization, and it works very directly with the outputs of the 3D software. Right, that is the end of this third tutorial. Thank you very much for your attention.